Hello everyone, and welcome to Module 2, Quick and the Evolution of the Web. With the background that we've had from the first module on the causes of latency on the Internet, this module will concentrate on a particular system run over the Internet, the World Wide Web, or Web for short. Although the web is not the only system run over the Internet, it is definitely the most popular and widely used. To begin with, this lecture introduces you to the technologies behind the web, an understanding of which is necessary to grapple with the origins of latency on the web, and also to understand the current efforts to reduce web latency and its effects on user satisfaction. We conclude this lecture by starting our journey into web latency, providing an understanding of the components that create web latency. In the following two lectures, we consider proposed and available techniques to reduce web latency. The first of these two lectures focuses on network-based or assisted technologies, notably WAN and session layer optimization techniques. The second of these lectures focuses on protocol optimization techniques, that is, optimization techniques that primarily concern the end nodes. Finally, the last lecture in this module is almost exclusively devoted to one particular technology, QUIC, that was introduced by Google already in 2012 and that aims to replace the TCP transport protocol altogether with something that significantly reduces web latency. Already popular websites such as Google.com, YouTube.com are using QUIC. Akamai started using QUIC on its media products in March 2018, and several others are expected to follow. Although QUIC currently only has a market share of 1.5%, it is expected to drastically increase its share in the coming years, not least due to the fact that QUIC is part of the next version, version 3 of HTTP, one of the key web protocols. The web, with its myriad of hyperlinked documents spread over servers all over the world, came to be in 1989, when Sir Tim Berners-Lee laid out his vision of what would become the web in his document, Information Management, a Proposal. The original motivation behind the web was basically to organize the information at the CERN particle physics laboratory near Geneva in Switzerland, the place where Berners-Lee worked at the time of his invention. By the end of 1990, Berners-Lee had conceived the three fundamental technologies behind the web: HTML, URL, and HTTP, and this became the start of what has become known as Web 1.0. Although the web became available to the general public already in 1990, it was not until Mark Andreessen and others at US National Center for Supercomputing Application (NCSA) released the web browser Mosaic 1.0 the web really began to flourish. The first websites were merely simple pages of words and pictures, i.e. essentially electronic documents. Moreover, it required a lot of expertise to create your own content on the web in these days. Sometimes that turns the content on the web to something for the few, not for the many. This shifted with the introduction of the so-called Web 2.0. Web 2.0 embraces an architecture of participation, a design that encourages user interaction and community contributions. Several popular blogs now compete with traditional media powerhouses, and many Web 2.0 companies are built almost entirely on user-generated content, for example Wikipedia, YouTube, Facebook, Twitter, etc. Although the term Web 2.0 was already coined in the end of the 90s, it really didn't take off until 2004 and 2005, and one reason for this was the introduction of the AJAX technologies that significantly improved the web user experience. We'll come back to this technology later in this lecture. The last milestone on this slide is a bit less clear than the rest of the milestones. Simply put, progressive web apps are applications that look and load like regular web pages but have extra functionality. These additions include the ability to work offline, so-called push notifications, and device hardware access. They can be bookmarked to a phone's home screen, launch without the browser user interface screen, and includes other features you typically associated with apps. The term progressive apps was coined by Francis Berryman and Alex Russell in around 2015, and is not a term encompassing a bunch of new technologies, but rather consists of a set of best practices to make web applications work similar to a desktop or mobile application. Now that we have become acquainted with the origin of the web, it is definitely time to get to know the web, how the web works and its underlying technologies. The basis of the web is transferring web pages from a server to a client. In its simplest form, that is, in Web 1.0, web pages are static. This slide tries to illustrate what happens when a web browser requests a web page from a server. As follows from the slide, it all starts with the browser creating a request for a given URL in HTTP. The URL is a shorthand for Uniform Resource Locator and is the technique used on the web to identify resources such as web pages, and the Hypertext Transfer Protocol, or HTTP, is the most commonly used communication protocol to send information over the web. The world get is an HTTP method that tells the web server that the browser on the web client wishes to obtain the web page, in this case http://www.k.se. After it receives the GET request, the web server retrieves the requested web page and sends the page back in an HTTP response message. Apart from a header with a status code that tells the browser whether the server handled the request successfully or not, it contains the content of the requested web page in the format HTML, Hypertext Markup Language, a representation standard for web pages that determines the syntax of a web page. As previously mentioned, HTTP is the primary transfer protocol that a web browser uses to interact with a web server. From a TCP/IP reference model perspective, HTTP is an application-level protocol. It is a simple, text-based request-response protocol that typically runs over the TCP transport protocol and determines what messages web clients may send to web servers and what responses the web clients may expect to get back from the servers. HTTP has 4 versions: HTTP 0.9, HTTP 1.0, HTTP 1.1, and HTTP 2.0, with the 5th one in the pipeline, HTTP 3. Today, the versions in common use are HTTP 1.1 and HTTP 2.0. With the inception of HTTP 1.1, the protocol is extensible and new functionality can be introduced by an ad hoc agreement between a web server and a client. HTTP is by itself stateless. There is no link between 2 requests being successfully carried out on the same connection. Still, while the core of HTTP itself is stateless, so-called HTTP cookies allow the use of stateful sessions. When receiving an HTTP request, a server can send a set cookie header with the response. The cookie is usually stored by the browser, and then the cookie is sent with requests made to the same server inside the HTTP cookie header. The management of connections against the web server is basically the responsibility of TCP. Before a client and server are able to exchange HTTP messages, they must establish the TCP connection. An HTTP method is usually a verb such as get or post, or a noun like head that defines the operations the client wants to perform. Typically, a client wants to fetch a research with get or post the value of an HTML form with post, though more operations are available. As mentioned in our discussion of how web browsers interact with web servers, Hypertext Markup Language, or HTML, is a representation standard that specifies the syntax of a web page. It is considered a declarative language, since it only allows the specification of what is to be shown in the web browser, not how it is to be accomplished. In fact, it is a markup language that it describes how web pages are to be formatted. To specify markup, HTML uses tags embedded in the web page, tags which consist of a term bracketed by less than and greater than symbols. Consider the example beside the text. The opening tag consists of the name of the tag, in this case P, wrapped in opening and closing angle brackets. This states where the element starts to take effect, in this case where the start of the paragraph is. The closing tag is the same as the opening tag, except that it includes a / between the tag name. This states where the tag ends, in this case where the end of the paragraph is. The opening and closing tags together with the content in between the tags is denoted an element. The term hypertext is an abbreviation HTML refers to so-called hyperlinks that connect web pages to one another, either within a single website or between websites. To make our discussion of HTML more concrete, let's consider a simple web page. The doc-type HTML declaration is used to inform a web browser that the document being rendered is an HTML document. While not actually an HTML element itself, Every HTML document should begin with a doc type declaration to be compliant with HTML standards. The actual web page content is provided between the HTML tags, the head pair of tag brackets in the page head, while the body pair of brag tag is the page body. Some tags are explicit commands for formatting. For example, the center pair of tags centers the bracketed text, the H1 tag specifies a first level header, and the P tag brackets a paragraph. HTML uses the image tag to encode a reference to an external image, and an anchor or a tag to introduce hyperlinks. That is the ability to link from one web page to another or to another location within the same web page. More on hyperlinks in a moment. As illustrated by the body, image and anchor tags, some tags have attributes that provide further formatting instructions. The BG color or background color attribute of the body tag specifies the background color of the body text. The SRC or source attribute of the image tag specifies the location of the image to be displayed on the web page, and the href attribute of the anchor tag specifies the hyperlink target. The web uses a concept called Uniform Resource Locator, URL, to specify the name of a web page, where it is located and how it is accessed. The general form of a URL is shown on the slide. Protocol is a placeholder for the name of the application protocol used to access the web page. Domain name is a placeholder for the domain name of the server on which the website resides. And finally, page is the name of the requested web page. As follows, the page placeholder may have one or several parameters. Many times URLs omit one or several parts of the general form, and if so, the HTTP protocol is assumed if protocol is omitted, and the so-called index page is assumed if the page placeholder is omitted. As already mentioned, HTML uses an anchor tag to provide a hyperlink capability. The way this is done, and which is illustrated on the slide, is through the use of a URL that specifies the hyperlink target. Cascading style sheets, or CSS, was introduced by HTML 4.0 in 1997 and supplied HTML with so-called style sheets that allows us to specify the presentation of tags on a web page. For example, fonts, spacing, sizes, colors, positioning, separately from the page's structure and content, that is section, headers, body, text, links, etc. In its most basic form, CSS consists of two building blocks: property and value. A property specifies which property you want to change, and value how you want to change the property. A property together with a value is called a CSS declaration. CSS declarations are themselves grouped into so-called declaration blocks, which together with selectors produce CSS rule sets. The CSS rule set illustrated on this slide basically tells the web browser to render paragraphs in color red. To illustrate the use of CSS, this slide shows how the format of a simple web page in HTML is governed by a CSS style sheet. As you can see, the style sheet makes the level 1 headers red and paragraphs black. Static web pages are in many ways a relic of Web 1.0. To better act as proper applications, web pages can no longer be static. They have to change during the course of the day or depending on how users interact with them. For example, consider yourself visiting the web page of your railway operator in order to book a train ticket online. What basically happens behind the scenes is the flow of events illustrated on the slide by steps 1 to 3. You fill in a search form to search for a suitable train departure. This results in a request being sent to the web server. A program is invoked by the web server, which generates a response web page that is sent back to you. The returned web page might itself contain programs that run in the browser. The program could, for example, be called upon if you would like to narrow down your search of departures. In this case, there is no reason to make an additional request to the web server, something illustrated by step 4. However, if you need to widen your search, then the local program will issue a new request to the web server, something happening in steps 5 through 7. When web pages are dynamically created by programs running on the web server, we talk about server-side or backend scripting. The first standard that enables server-side scripting is called Common Gateway Interface. And although CGI was not standardized until 2004, it has been around since the birth of the web in the early 90s. CGI is not itself a programming language, but an API that lets programs written in various languages act as server-side scripts. The only requirement is basically that the language could read and write to from a console window, that is, standard input and standard output. Nowadays, there are easier ways to do server-side scripting. A popular scripting language is PHP, which is an integrated interpreted language and thus requires a PHP interpreter to be installed into the web server. Microsoft has its own framework for building server-side script called ASP.NET, a framework that is heavily integrated with their Internet Information Server, but which on the other hand is very versatile and offers scripting in most languages that run on the .NET platform, including C# and Visual Basic. In the past several years, it has also become very popular to do server-side scripting in JavaScript, the primary language for client-side scripting on the Node.js platform. The server-side scripts are excellent at handling access towards databases. However, they are less apt for user interactions such as mouse movements and user input validation. This is where client-side scripts come into play. They enable the design of responsive web applications and removes the requirement of constantly issue requests against the web server. Smaller JavaScript programs are typically embedded in the HTML on the web page, while larger programs are placed in external files. JavaScript is by itself a cross-platform object-oriented language that provides access to the web browser through what is called the document object module, more on this later, and provides access to numerous other services through different APIs, for example audio, video and geolocational APIs. One popular way of combining existing dynamic web technologies is AJAX, asynchronous JavaScript and XML. The design of an AJAX application differs from traditional web applications in that it introduces an intermediary between the web browser and the server, an AJAX engine. When an AJAX application is loaded into a web browser, an AJAX engine is loaded that is responsible for both rendering the interface and communicating with the web server. The benefit of introducing an AJAX engine is that it disentangles the user interaction with the web browser from the interaction between the web browser and the server. That is, it enables user interaction to be asynchronous with the server interaction. In other words, the user does not have to stare at an hourglass every time access is made against the web server. The slide illustrates the difference between a traditional web application and an AJAX ditto. Particularly note step 4, page reloading, in the figure illustrating a traditional web application. During the reload, new user interaction is possible and the application seems unresponsive. In contrast, in the figure illustrating an AJAX application, a new request is possible in step 3 in spite of an already outstanding request, step 1. As mentioned in the beginning of this lecture, the term progressive web app was coined by Francis Berryman and Alex Russell in around 2015. The term progressive is included to emphasize two things. First, it is a web application that progressively becomes more and more like an ordinary native desktop and mobile application. Second, that the web application experience progressively improves with more capable web browsers. Although there is no precise definition of what is needed to be a progressive web app, there seems to be an agreement on that it at least needs to have a so-called web app manifest that provides a meta information about the app, for example icon and name of the app, and so-called service workers. Service workers are basically event-driven daemon processes that run in the background of a web application. In the same way as an AJAX engine, they are called the process activities in the background. As illustrated in the figure on the slide, a service worker is able to cache content locally and use this content when the network connectivity is poor or absent. We conclude this lecture by initiating our study on web latency. To begin with, we should acknowledge the fact that web latency has indeed a measurable effect on user engagement. Research suggests that 1 in 4 visitors would abandon a web page if it takes more than 4 seconds to load, and 40% of e-consumers expect page load times of less than 2 seconds. The question still remains, how do we perceive latency? And the table on the slide is an attempt to answer that question. We note that everything below 100 milliseconds is essentially perceived as happening instantaneously. Google researchers suggest page load times of less than 100 milliseconds give visitors the illusion of instantaneous website response, as the visual sensory memory processor in our brain works in bursts of 100 milliseconds. We also note that a 1 second delay many times could be acceptable, since it is still short enough for a person to maintain a seamless flow of thought. On the other hand, a 10-second delay generates a strong frustration and will most likely keep visitors from revisiting the web page again. Since we already know that the important contributing factor to web latency is the amount of HTTP requests being made by the web client to the server, not least this is obvious by developments such as AJAX and progressive web applications that try to decouple user interaction with the browser from the browser's interaction with the server, it is interesting to study how the figure has evolved over time. The top graph of the slide plots the median number of requests in total that a web browser carries out against a web server when displaying a web page, and covers the period January 2015 up to January 2019. The blue graph shows the number of requests happening when a web page is displayed on the desktop, while the purple line shows the number of requests on a mobile unit. We see that although the number of requests recently started to decrease, it is still on levels of 70 requests per page. Since many of these requests can be done in parallel, it is not altogether straightforward to compute the number of sequential bursts of requests this corresponds to. When a web browser is to display a web page, it scans the HTML for resources to download. Often these resources comes from a single domain, and web browsers typically limit the number of concurrent requests to 6 per domain. This gives us 12 sequential bursts of requests. However, in order to reduce latency and increase concurrency, a domain is often split into several subdomains, and browsers distribute their requests over all these subdomains, something called domain sharding. Thus, the number of sequential bursts of requests is probably 40 to 50% less. However, as shown in the bottom graph, this still leaves us with medium display times of around 2.5 seconds on the desktop and as much as 5.8 seconds on a mobile unit. Before delving into the details of what causes web page latency, it is beneficial to have at least a conceptual understanding of how a web browser works. The left figure on this slide shows the main components of a modern web browser. The user interface includes the address and toolbars, the menus, etc. That is everything you see in a browser except the window showing the requested web page. The browser engine manages the communication between the user interface and the rendering engine. It is the rendering engine that is responsible for the window showing the requested web page. For example, the rendering engine parses HTML and CSS and displays the parsed content in the web browser. To be able to save data locally, a web browser has its own data storage or database. Among other things, this data storage is used to save cookies and offer local storage for progressive web apps. Apart from these core components, a web browser has a number of subsystems. For example, networking and JavaScript. The networking subsystem provides a platform-independent networking interface for the rendering engine. Thus, the rendering engine does not have to be concerned with the intricacies of different operating systems. What the JavaScript subsystem is doing should be self-evident. The right figure illustrates the steps taken when a web browser displays a web page. The rendering engine starts parsing the HTML and starts creating a document object model or DOM tree. The DOM tree is an internal representation of the web page, with the root node representing the complete web page, intermediary nodes representing header and body parts, and the leaf nodes representing the individual elements, for example an image or some text. In parallel with the parsing of the HTML, the CSS is parsed and a complementary CSS object model tree is created. Next, the content of the DOM and CSS trees are combined into a render tree. The render tree contains the visual elements in the order in which they are to be displayed. Still, the exact placement of the visual elements takes place during the layout step. In the final step, the painting step, the render tree is traversed and each node in the tree is displayed in the browser window. With knowledge about how the web browser works, we are in a position to study what happens from that a web page is requested until it is fully rendered or displayed on the screen. To do that, we use an online tool called WebPageTest. WebPageTest is a free tool that generates a so-called resource waterfall for a web page, basically a Gantt chart over all activities taking place when a web page is loaded and displayed. This slide shows the resource waterfall for the information web page of this course when loaded and displayed on a desktop in Stockholm. First, consider the green and blue vertical lines in the resource waterfall graph. They show that although it took a bit more than 7.5 seconds to completely load the page, the rendering of the page started long before that, in fact already after less than 1.5 seconds. In this way, the web page still feels responsive, although the actual page load time is quite significant. Next, note that we have several HTTP requests being issued in parallel. As the content of the web page is being fetched, new requests are being made. Thus, the scheduling of when a resource is fetched is largely determined by the structure of the web page. The browser may prioritize the retrieval of some resources. However, the incremental discovery of each resource on the web page is the main reason for having a resource waterfall. Finally, it could be noted that almost 6 seconds out of the total page load time of 7.5 seconds comprises download and execution of JavaScript, something that is an effect of Costa University making use of the Drupal Web Content Management Platform, a platform that makes heavy use of JavaScript. Before concluding, let us summarize what has been brought up in this lecture. To start, we trace the origins of the web or to the late 80s and 90s. In the beginning, the web only consisted of geographically dispersed hyperlinked static web pages, something today known as Web 1.0. Later, in the midst of the first decade of 2000, dynamic web pages and technologies such as AJAX entered the screen, something that transformed the web from being a platform where a knowledgeable few generated content to a place where basically everyone could be their own publisher. Web 2.0 was born. At present, we are in the middle of a period where more and more of the services provided on the internet are provided as progressive web apps. That is, web applications that are essentially indistinguishable from native desktop and mobile applications. Next in this lecture, we went through the principles behind Web 1.0 and its key underlying technologies: HTTP, HTML, URL, and CSS. This was followed by key technologies behind Web 1.0's server and client-side scripting, AJAX, and more recently, service workers that underlies progressive web apps. The lecture concluded with an introduction to web latency. We briefly discussed how users experience latency, how the latency of modern web applications can be traced back to its traffic characteristics, and finally, how the so-called resource waterfall is able to give us detailed knowledge about the origins of latency for a specific web page or web app. In the coming 2 lectures, we will continue the techniques available to reduce latency. In the meantime, bye.